Welcome to the course on power quality. So, we are discussing the solar case or grid interface solar PV system. So, we would like to have now discuss some example with the numerical problem. So, starting from first example, design a two stage single phase grid tied solar PV inverter to integrate 4 kilowatt peak power of PV array with a single phase grid, and circuit topology consists of a boost converter and edge bridge voltage source converter. So, this is the typical circuit. We have a boost converter, I mean here with the for maximum power tracking, and we have an inverter to feed this power to the grid. And coming to the design and selection of DC capacitor voltage. So, the range of variation of AC side voltage for this system is considered from 170 to 270, and the DC link voltage is almost 10% higher than the AC voltage to compensate for the drop for devices interfacing inductor and second harmonic ripple in single phase system. Therefore, the DC link voltage is selected here 1.1 into root 2 your RMS voltage there. So, after putting the value like 1.1 root 2 into 270, that is the maximum voltage is given here, it comes 420 volt. And now coming to design of capacitor. So, the you can call it instead power in single phase system consists of second harmonics and ripple. This ripple is in power is also reflected on DC link voltage. Considering the ripple design of this, so typically this is I 0 upon 2 omega VDCR, and where the I 0 is a capacitor current, omega 0 angular frequency, and VDCR the ripple voltage of capacitor. Considering the 2% ripple over the DC link voltage of 420 volt, so it comes 8.4 volt, and considering this 4 kilowatt power at DC link of this much current of 9.52, so CDC is obtained as typically putting the value 1804.7 microfarad, and it is selected usually little higher than around that, so it is 1800 microfarad. Now, coming to PV array design, the PV array is connected at the input terminal of DC-DC boost converter, the output of boost converter connected at the DC link, and therefore, PV array voltage rating is so decided that the open circuit voltage equal to the your minimum voltage, and the minimum DC link voltage is typically 1.1 into root 2 VSM, and this comes typically or 1.1 root 2 170, so it comes 264, and that is why PV typical voltage taken 270 volt. Now, for this solar cell has open circuit voltage, each solar cell of 0.62 volt and 3.6 ampere of short circuit current. The active power typically is your equal to number of the series connected cell into the voltage maximum power point voltage of one cell, then the cell connected number of cells connected string in parallel, and the sort typically maximum power current. So, that is equal to 4 kilowatt, and normally the maximum power occurs on the 90% of the open circuit voltage and 90% typically of the short circuit current. So, from that having a value of MPPT current of 3.24 and MPPT voltage of 0.558 of each cell, where NP and S represents the series and parallel string of PV cell. So, putting typically the value, so we get typically from this 270 volt with this voltage we get typically 436 cell series, and then considering open circuit voltage of 270 volt. And coming to the current calculation, so maximum power divided by this open circuit voltage into 0.9, so it comes a current comes MPPT current comes 16.46, and now considering the current for each number of cells, so it is coming to the 5. So, PV array for 4 kilowatt capacity is now with 5 cells, 5 string of cells connected in series and 436 cell in each series to form the PV array of 5 into 436 cells solar cell. Now, coming to the selection of boost inductor, boost converter inductor. The boost converter designed based on the allowable current ripple, and the current ripple in the boost inductor is dependent on the input and output voltage of the boost converter. In this case, boost converter is designed to considering the input voltage of MPPT at 1000 watt per meter square, and the output voltage of DC nominal, and the DC link voltage we know the DC link 1.2 into root 2 Vs, so it is around 360 volt, and the MPPT voltage of PV array is 90% of this. So, that comes typically 240 volt, so from which we get the duty cycle, and putting the value it comes 0.33%. And now, from this relation we can find out the value of the boost inductor from the input voltage and on period, where the whole PV voltage input voltage short circuit across the inductor and the ripple current and the switching frequency. So, considering the voltage corresponding to MPPT 240 volt and duty ratio of 0.33, switching frequency of 10 kilohertz, and IM peak ripple current in the boost inductor is calculated around consider 10% of the current of this PV array, that comes 3.34, and now putting the value of in the relation, so it comes 2.36 37 millihenry, and we select 3 millihenry for this boost inductor value. Now, coming to the selection of devices for voltage source converter, the maximum blocking voltage is 420 volt based on the DC link voltage. A safety factor of 4 is considered to accommodate the high frequency ripple switching, and therefore, the voltage rating of the devices is 1.4 into Vd. So, it comes like a 588 and we select the 600 volt, and similarly for the current we calculate the current maximum current from typically power and voltage. So, we get to 23.52 and the switch current with the 20% factor with the peak current we get 39.87. So, and coming to selection of interfacing inductor of the inverter, it comes PSC into MVDC upon 4 single phase inverter, and considering the 10 kilohertz switching frequency, modulation index 1, DC link voltage of 360 and overload factor of 1.2, current will 10%, the value calculated is 3.15 and we select 3.5 millihenry. Now, coming to selection of ripple filter RCCR, that is we consider corresponding to half the switching frequency, where TSC is the period for switching frequency, which we consider 10 kilohertz, and we select the typical value of this resistance of 5 microfarad and the capacitance comes 5 ohm, and we select capacitor obtain 5 microfarad, and this offers a very low impedance for switching frequency around 5 ohm, and at low frequency, at fundamental frequency it offers even 300 ohms. So, that you are not having the losses in ripple filter. So, coming to the question number 2, a 2-stage solar PV conversion system integrated with single phase supply of 240 volt 50 hertz. The grid has the following specification: open SP module will have a 36 open circuit voltage, then the short circuit current level 7.84 and series module are 8, and the MPPT voltage is 29 volt for module, and the MPPT current is 7.3 and 2 strings are connected in parallel. The PV array is operated at the maximum power at 0.4 1000 watt per meter square and 25 degrees Celsius. Calculate the RMS current injected into a grid, assuming the losses, negligible losses power injected in the grid at unity power factor. This is a typical system and we have given here, and we want to calculate the current here. So, we can find out the virtually the typically the PV voltage, that comes NP into V, that is 232, and PV current that is virtually from string to 14, and the PV power of 3410 watt, and the considering the negligible losses, this will be equal to your RMS voltage, RMS current. So, that at unity power factor, so it comes to that, and we can find out, once we know the voltage, we can find out the current unity power factor current from this relation P divided by Vs, that comes 14.21 ampere. Coming to example 3, a 3.8 kilowatt solar PV array is connected directly at the DC link terminals of the voltage source inverter integrated with 230 volt single phase grid, and a 240 volt battery bank is integrated at the same DC link terminals using the bidirectional DC-DC converter, and the control scheme is designed to feed a constant 2.5 kilowatt power to single phase grid at all time. Calculate the battery current when the incident solar irradiation is 1000 watt per meter square. Also calculate the current injected to the grid, assuming unity power factor operation at the grid side and negligible losses like. So, coming to the solution part of it, it is 1000 watt per meter square. So, as solar photovoltaic array generate the 3800 watt, and power flow in the grid is typically 2500 watt. So, the typically the battery power is Pg minus Pv. So, it comes like a typically your 1300 watt, and now the battery current, because battery voltage is given to you from power, we get the battery current of 5.42 ampere, and we get the typically the current into the grid power divided by, that is the power virtually into the grid divided by its grid voltage. So, it comes 10.42 ampere. Now, coming to example 4, a design a 5 kilowatt 3 phase 2 stage solar PV grid interface system. So, we have a 2 stage system solar PV generation, and then we have an inverter feeding to the grid. So, coming to typically the proposed system designed for peak power of 5 kilowatt at 415 volt, and solar PV module source is 3.8 and open circuit voltage 21. So, we can have a maximum power from 5 kilowatt here, and where the NS and NP represent the series and parallel strung of PMPPT the voltage of the module of the MPPT, and IMP the current of the typically at MPPT, and PMP is the nominal power. So, PMP is generally calculated to achieve by NS into 85% open circuit voltage and NP into 85% short circuit voltage, that is 5 watt, and IMP 3.3 and VMP 17.85. So, ideally open circuit voltage of PV array should be approximately equal to DC link voltage. However, due to the rating constraint of PV array, the 600 volt is used. So, PV modules connected in series are calculated from open circuit voltage into this number of strings. So, from this 600 we get the 28 module connected in series, and from the maximum current we can calculate from the power. So, we get the 9.8, and we can calculate the typically you can call it module connected in parallel string of 3 modules. So, therefore, a 5 kilowatt peak power capacity is designed with 3 modules in parallel, 3 string in parallel and 28 module in series in each, and this make the array of 3.3 into 28 modules. And the design of DC-DC converter corresponding to with the duty cycle of 0.2. So, we can get the interfacing inductor value from MPPT voltage with duty cycle and ripple current. So, we get 6.07 millihenry. The I1 is the ripple current, is considered 20% of DC link DC boost converter inductor current, and we can find out the inductor current from MPP. So, it comes 8.4 ampere and calculate IP is 1.68, thus the inductance value selected is 6 millihenry. Now, the design and selection of DC link capacitor voltage. So, capacitor voltage is calculated from this relation of where line it is a line voltage divided by modulation index. So, putting the value we get 703, we select the 700 volt where L is the typically the VSC AC line voltage and M is the modulation index, and the interfacing inductor for this is calculated based on the ripple current, switching frequency and DC link voltage from typically this is standard relation for 3 phase of grid interface relation. Putting the value we get 5.5 millihenry where the ripple current is considered 20%, switching frequency of 10 kilohertz and overloading factor 1.2, and LF is selected 5.5 millihenry. So, coming to selection of DC link capacitor. So, DC link capacitor is calculated from energy balance equation. We allow the voltage to go down from 700 to 680, and we have to recover virtually corresponding to typically in 5 milliseconds. So, its capacitor comes 2231.5 microfarad, and we select the next capacitor value of 2200 microfarad. So, coming to example number 5, a solar photovoltaic array integrated 3 phase 415 volt 50 hertz and DC boost converter voltage and a voltage source inverter have the following specification. The open circuit voltage of module 30.6 volt and MPPT corresponding voltage is 29, and a short circuit current is of each module of 7.84 ampere. So, MPPT current 7.35 ampere, and series modules are 14 and parallel strings are 8. So, if the DC link voltage of VSA is maintained 700 volt, calculate the duty ratio of boost converter required to operate the PV array at maximum power point of 1000 watt per meter at 25 degree Celsius. These are typical configuration that we have a solar PV array with the boost converter, and we have an inverter interface to the grid like. So, coming to the solution, that solar PV array is operating at 1000 watt per meter square at 25 degree Celsius, and solar PV array voltage for operation at the maximum power point is calculated from series, typically the number of series modules and MPPT voltage of one module. So, it comes 406 volt, and now we can find out the duty cycle from the relation of this boost converter. And now duty cycle calculated from DC link voltage and PV array voltage by, so it comes 0.42. Now, coming to the sixth example, a multifunctional 30 kilowatt single stage rooftop solar PV photovoltaic system is integrated with the 415/50 hertz 3 phase grid using a voltage source inverter. The complete solar energy conversion system is connected with a linear load, drawing 15 kilowatt power at a unity power factor of 0.8. Calculate the voltage, current and kV rating of the inverter of the solar energy conversion system to provide reactive power compensation. So, these are systems that single system. We have a solar PV array, we have an inverter, we have a local load which is here lagging power factor load. So, we want to have unity power factor current of the supply. So, inverter is supposed to provide the reactive power along the active power to the grid line and as the active power of them. So, the supply voltage is given 415 volt line. So, we have a phase by root 3. So, it comes to 39.6 volt and frequency is 50 hertz, and active power is equal to P equal to 15 kilowatt, and reactive power the load is your Q1 P1 tan phi. So, you get 11.25 kVR, and also voltage source inverter is used for reactive power compensation. So, reactive power through CI is virtually this reactive power of load 11.25, and assuming negligible losses typically the active power flow through the is the 30 kilowatt. So, V rating of the inverter will be Q square P square. So, it comes 32.04 kVA. and voltage rating of the VSI is typically 239.6, which is the grid voltage, and the current rating of inverter is from power 32 to kVA 32,040 VA divided by 3 into the voltage. So, this comes 44.57 ampere. Coming to the 7th example, a single stage grid connected 3-phase solar photovoltaic system is supplying a linear load of 2 kilowatt at 0.5 kVAr, and grid is operating for 15 volt and 50 hertz. The solar PV operating is 750 volt at 10 ampere. At the maximum power tracking of 1000 watt per meter square, and the MPPT maximum efficiency of PV array is observed to reduce the according to typically this algorithm, where the x c is the efficiency of the gain parameter holding a value of 0.04. The voltage source converter control scheme ensure the grid always operate at unity power factor. The voltage source converter losses can be also assumed for 5% of its power. Estimate the load current A and the grid current under the this current MPPT operation 1000 watt per meter of PV array, and B figure out the grid power factor and the phase shift in the VSC phase current with the phase voltage. So, this is the system of single stage. We have a PV inverter, we have a load, and we have the grid. And coming to solar PV array operating at 750 volt and 10 ampere. So, net power supply is 7500 watt, 7.5 kilowatt, and considering the inverter losses 5%. So, net active power supplied is 0.95 into 7.5. So, that will be 7.125 kilowatt to AC, and the load active power is 2 kilowatt. So, net power fed to the grid is your typically 7.125 minus 2 kilowatt of load. So, it comes 5.125 kilowatt. So, since the grid voltage is 415 line to line RMS, so line current flowing to the grid will be your S divided by root 3 line. So, that is putting the value of your typically your active power and reactive power of the, that is the typically the load line current, I mean from it comes 2.87, and we can find out the grid line current for line RMS. So, we have a power active power divided by root 3 line. So, we have active power and then we have a voltage. So, we get 7.313 ampere. So, it is noteworthy that only the 3-phase active power is considered for calculating the grid line current. This is because the VSC is ensuring the unity power factor always, otherwise net accident power needs to be considered. So, since the voltage source converter needs scheme ensure that the grid voltage is operated at unity power factor, the grid line current are always in phase with the corresponding voltage. And however, in this case, the since power is being fed back to the grid, so grid power factor is negative, thus the grid power factor is -1. So, owing to UPF operation of the grid, the voltage source converter supply total reactive power of 0.545 kVAr. So, since the active power through VSC is 7.125 kilowatt, so phase shift in VSC phase current with respect to the voltage will be the angle between corresponding to active and reactive power, and that comes 4.014 degree for fundamental. Now, coming to the typically the 8th example, compute the load current and the grid current in previous question for solar PV insulation dipped to 600 watt and load increases by 2.5 kilowatt and 1 kVAr. The MPPT algorithm efficiency of PV array observed to reduce the insulation increase according to the equation, where efficiency is corresponding to 1 plus C under root 1000 x to power 4 minus 1. So, where C is the efficiency gain parameter holding a value of 0.03. After change in insulation, the estimate the grid power factor and phase in shift in the VSC phase current respective of the phase with respect to the phase voltage. The PV array is operating at 750 volt with the solar PV insulation of 600 watt per meter square. So, this is the configuration of single stage system with the solar inverter, and you have a load here interface to the grid. So, coming to numerical part, here the solar PV array is operating at 750 volt, but not at 10 ampere. Ideally, the power supplied by the PV array is directly proportional to the solar insulation. So, we can say corresponding to 600 typically 600 watt per meter square compared to 1000 watt per unit marker, you can have a 0.6 into 7.5. So, it generates the 4.5 kilowatt. However, since the efficiency of MPT algorithm varies with the insulation, so net power extracted from this relation, I mean we can calculate from this. So, it comes typically 9.93 into 4.5, so it is 4.185 kilowatt, and considering the inverter loss is 5%. So, net active power supplied will be 0.95 into 4.885, that comes 3.976 kilowatt, and the load active power is 2 kilowatt plus 2.5 kilowatt, so it is 4.5 kilowatt. So, net power fed to the grid is your typically this load power minus this solar power minus the typically the load power. So, it is a minus 0.5, the active power is being drawn from the grid. So, since grid voltage is 415 for line to line average, so line current of the load can be computed from this typically from kVAR from the VR from the voltage divided by the √3 line voltage. So, it comes 6.6 ampere, and since the grid is a again 415 line to line RMS. So, line current for typically for the grid is power drawn from the grid into √3 times line voltage. So, 4.5 kilowatt or 500 watt divided by √3 415, it comes 0.9696. This current is coming from the grid towards the typically load. It is worth noting only that 3-phase active power is considered for calculation of grid line current. So, this is because the VSC is ensuring unity power factor always, the whole 3-phase apparent power needs to be considered otherwise. So, since the VSC control scheme ensures that the grid always operates at unity power factor, the grid line currents are always in phase with the corresponding voltage, and in this case since the power is being given by the grid and the grid power factor is positive. So, since the grid power factor is +1, owing to the UPF operation on the grid, the VSC supply load reactive power of 1.5 kVAR, and since the active power of the through VSC 3.976 kilowatt. So, the phase shift between VSC current and with respect to this it your phi equal to tan inverse Q upon P, and from this calculating it comes 20.67 degree. So, with this we would like to now summarize the solar grid interface system. So, as a case study, the classification and design of various voltage source converter, single phase, 3-phase configuration for solar energy conversion system have been investigated for feeding the solar PV power into the grid, where the solar energy conversion systems include the conventional PV inverter as well as the multifunctional voltage PV voltage source converter, which simultaneously help in power quality improvement, and the performance of various single stage 2-stage configurations are evaluated. Like the control and implementation of single phase 2-stage grid type solar PV system have been achieved, and a boost converter is used for maximum power tracking, and a single phase bridge voltage source converter is used for grid interfacing power converter, and simple control and implementation system and multifunctional are carried out under nominal and non-ideal condition, and the control and implementation of single phase single stage tight system conversion single base PV inverter and multifunction are carried out under the nominal and non-ideal and grid voltage condition. So, control and implementation of 2-stage 3-phase wired system are made. Boost converter is used for MPPT of 3-phase voltage source converter, used as a grid interfacing power converter, and novel control and implementation of 3-phase PV inverter and multifunctional solar are carried out under nominal and non-ideal condition, and control and implementation of single stage 3-phase power with the single phase inverter and 3-phase 3 lag voltage with load compensation are carried out, and the control and implementation of 2-stage 3-phase 4-wire grid tie system are realized. A boost converter is used for maximum power tracking, and 4 lag VSC is used for grid current interfacing power converter. So, this system not only feeds the solar power into the grid, but also helps in power quality improvement of 4-wire distribution system, and control and implementation of single stage 3-phase 4-wire grid tied solar energy conversion system using a 4 lag voltage source converter based system configuration are carried out, but the VSC not only serve for the MPPT, but also help in power quality improvement of 4-wire distribution system, and the control and implementation of power quality improvement technique for solar power photovoltaic system are operating under both grid connected and external system. Similar transition capability also carried out, and these are the some of the references which are used in this, and thank you.